first afternoon session of the HOPE workshop. My name is Gabriel, and right now we have a talk that addresses one of the problems that probably everyone in this room has to deal with if you try to implement decent programming language that has binding. So, and binding is particularly difficult when it's nested and it goes within other data structures. So Gabriel Scherer is going to tell us about how to solve this problem.
Okay, thank you. So this is work done mostly not by me, again. I'm going to talk about work that was done in the largest part by Scherer as a PhD student of Dale Miller, and they are both working in Saclay, which is a small city in the suburbs of Paris, where I am, and so we are colleagues. And I started more recently collaborating with them on this project that I'm going to talk about. Okay? So the idea is to talk about MLTS, which is an ongoing language design experiment. So it's very work in progress. Some details change, and in a sense, what I'm going to present you is a future version of the language compared to what exists in the implementation, for example. And the idea of MLTS is to extend ML, the programming language, not machine learning, with constructs to handle binders, so names, coming from the Lambda Prolog community, from the logic programming community. Okay? Because Dale Miller and Scherer have worked on Lambda Prolog and also the proof assistant at Bella, and I thought, okay, what could these ideas bring to the ML community? So it's a bit different from what has been done on binders in the ML community, and I will mostly focus on presenting what is there rather than the component. So the theory, or the key idea, is that when you do logic programming, computation does not come from reduction of a proof, cut elimination, as in the way we usually present functional programming, but it comes from proof search. Okay, so you write a goal such that doing a search for the proof of the goal is the computational process that you want to run. Okay, and so in this community, one fairly natural way to handle binders is to add a new quantifier on the logic. So this has been done in particular in Lambda Prolog, which has this nabla x quantifier, which means, in a sense, not for any x or for some x, but for a fresh x, which is kind of a mix between, it's not any x, but most of the x's and at least one. So, okay, it's a kind of okay, you don't need to think about proof search in the talk, but the idea is they have this support for binders that is rather natural, easy to justify from a logical perspective. So what does it give if you add it to ML language? There is an implementation that is done by compilation to Lambda Prolog, and hopefully I'll talk a bit about that. And you can find it online, it's very cool. And summary, to kind of kill the suspense, it looks a bit like a funny mix of fresh ML, if you know, and higher order abstract syntax. I should say now that they would not like if I call it higher order abstract syntax because they are not fond of this name. So they call it instead the lambda tree syntax, okay, so which are the LTS in the name. And one idea that I will come back to is that you don't talk about free variables or about variables very much. You talk about binders, and they move. They move in the term during the computation. So binder mobility is one of the ideas that this community likes to insist on. Okay, feel free to interrupt me at any point during the talk. We have plenty of time, and I will probably finish in advance. So in MLTS, the idea is to extend the data types, the algebraic data types of ML, with binders. So from an MLTS point of view, if you think of a normal ML data type, it represents closed values, okay, that do not contain binders. And then you can we add new syntax that lets you define open data types which do contain binders. So here's an example. This is a type of that represents terms in the untyped lambda calculus, okay, NAM. So a term is either an application that has two parameters, left and right hand side, or an abstraction with this type. So this is not the arrow type of ML. We try to call them thick arrow during this talk. This means a lambda term under a binder of a fresh variable itself representing the lambda term. So which is the way when we write lambda x dot t, when we give a name to the x, it's a binding position. And so this is what this lam on the left means. One thing to notice is that there is no constructor for variables. Okay, so if you know about fresh ML, for example, there would be a case for variables here. The idea is if you, at some point, you talk about a name, the name of such a type introduced, for example, by this binder, you can think of it as another value that is not any of these two constructors. So here are some examples of inhabitants of this type. So what we know, I mean, if you want to look at this term, the identity lambda term, you would write it that way: apps x to x, and this. So this is the introduction form for this thick arrow. It's an infix operator, and that means that the thing on the left is the binder, and the thing on the right is the term under the binder. Okay, so lambda x. Feel free to come closer. You know, there are some seats. I see some people in the very back getting a telescope to watch the screen. Okay, so for example, lambda x applied to x is just add x to add x, and so on and so forth. So nice and easy. This is syntax that comes from lambda prolog, but was repurposed for slightly different. Cool. Okay, so now I'm going to show you an example of MLTS program to kind of get you in the water before you know how to swim. So let's implement substitution with this shape. So I will take two lambda terms, sort of assume that the second one is a variable, and then I will return the substitution. So subs t xu should be t where all the occurrences of x have been replaced by v. Okay? So pretty common operation to define on types that represent data with names. Okay? So to implement subs of t xu, I will pattern match on x and u and t. Why both? Because sometimes you want to compare them to know if the t is actually the same thing as x, which is the first case. So new syntax coming up, nab x, and that means, okay, if for fresh name x that I didn't previously know about, so that means if there is a name x such that what I'm matching is the pair xx, then return u. Okay, what this means is that, well, if t is exactly the variable x, which is the same as x, return. Okay, so yes, so yes, this means, okay, if for two fresh variables xy, then what I'm matching is xy, returns y. So first, when I say, so nab or nabla, when I say nab xy, implicitly I'm assuming that they are distinct. Okay, and it's an invariant in MLTS. When you have when you introduce a name, you always assume that it's distinct from everything else. Okay, and here notice that the y that was introduced here is in scope here. So this nab construct, it's not a pattern construct. You cannot nest it deep inside a pattern. It's something that you can add to a clause, so something of the type p arrow e. You can add a nab in front of that, and this goes both over the pattern and over the right hand side of the clause, the matching clause. Okay, and then the rest is kind of easier. If okay, you have x and then add mn, you just recurse under the application. Yes.
Question just to build intuition
yes.
about Nabla, which I don't have. How similar or different is this from Gabay and Pete's and quantifier for finding the fresh name?
So I think they are similar in usage, but different in the theory of how they are justified. But I'm not familiar enough with the theory of either of them to give. So I think Gabriel piece is nominal sets.
Mm-hmm.
So the most important operations are swapping names, which is like FreshML was at first. I mean, the first version of FreshML was pretty much an implementation of that. Whereas the naming support here comes from the theory of the Nabla X in the logic programming community, which is different. But I'm not familiar with the details of it.
So when you say X and Y are fresh, they're fresh with respect to
yeah.
what?
So yeah, I'm not saying that I'm making fresh names. What I mean is, for names X and Y that are fresh, that are not known by me in the current context. So names coming from the outside. So you can think of it for some name X and Y, but they have to be distinct with each other,
yep.
and from other nominals that I have introduced myself. So I'm writing a function, so I may be called in code that I don't know, and this code may have binders that are bound at places I don't know about, and it is these binders that NAB is capturing.
But if I'm... Okay, I'll talk to you offline about it,
okay.
Sorry.
The last case, I think I have some type derivation here. Yes, X. So when I write X and halves of R is not a term, it has this type lam to lam, okay? Thicker or lam. So then what I should write here is the same, something of type thicker or lam. So here I'm abstracting over this variable y, and then here, because this is a lam to lam, this is the application form for the Figaro. I'm going to come back to that. So this has type lam. The whole thing here has type lam. So when you abstract over it, it's lam to lam again, and you can plug it into apps, and you get a lam. So I remove the subs thing here, but it doesn't change it. Okay. So which is to say, I'm binding a variable at this Figaro type, and then I'm opening and closing again a binder here. And one way to think about this, which is here, is that so the operation here, I'm opening a binder y at this position, and then I'm kind of plugging it into R. One other way to think of it is that I'm moving the binder that was in R here outside to an outer scope. Okay, so I'm not opening a free variable and plugging it somewhere. I'm moving a binder from somewhere to somewhere higher up in my term. Yes?
So I noticed in the last line there is no nav cap y.
Yes.
Why?
So here I'm talking about names that come from the input that I'm matching over, and here when I'm doing this, I'm saying, okay, it's an abstraction, so there is a binder, and I am introducing the binder with this construction. So this is the term that binds the name y, and then whose body is this. Okay? And then so in the body I can use y, which is bound here.
And then if you do this, it will match the nav one. If you use y,
I couldn't say here, well.
Yeah.
No, there would be an example.
Match the other clause, right?
Oh yeah, it could. Well, it could match one of the other clauses, except for the fact that these two clauses that use a nabla only match a free variable on the right hand side, not an at as I'm written in here. But yes, and there will be more examples of fun with patterns and these constructs. Other questions?
I have a quick one.
Yeah.
So this pattern match is non-exhaustive. Is this a simplification for our purpose, or is this an actual problem?
So is it non-exhaustive?
Well, it's a lam into lam into lam, and you're not. Like, what if x is not a variable?
Oh, it's non-exhaustive on x?
Yeah.
That's a good point. Yes. I was thinking of it's exhaustive on T, but
It's exhaustive on T, but not on X.
So yes, it's not exhaustive. I will talk about the fact that it's hard to do exhaustiveness in this sequence in the end. And then I will also show a version of self that is better behaved from this point of view. Yes, people coming to the front. Excellent. Okay. So so the idea was to show something first and then explain later, which is how I like to be introduced to language constructs, but maybe not everyone, to apologize. So to come back to it, A thick arrow B means it's a term with a body of type B under a binder of a variable of type A. Okay. You can think of it as an arrow type, but it's not a function that computes. It's just a binder position, so it's not really an arrow type. And there are introduction and elimination forms, which I've used already. I noticed that the right-hand side here is restricted to a variable, okay, and not an arbitrary term. Even though this design choice has evolved, and you could give a meaning to an arbitrary term here, it would be a sort of substitution. But the fact that you only use names here gives you a very simple theory and efficient implementation. So I've already talked about this. I probably don't need to come back. Here is an example of a function in ML that takes an argument that has a thick arrow type. Okay, and you can also have typing rules for these constructs, and they are, as you would expect, very simple. Nothing very complex from the typing point of view. Again, I'm restricting the right-hand side to be a nominal, which is the way I call this kind of constructor-looking things that are variables in the domain and are stored in the context. And you can use, you can use these two constructions in patterns, and there they get interesting and new, different from what you typically do in the. Yes, Phil.
So you're only allowed to write T at X.
Yeah.
But the type of T is lam and the type of big X is lam. So how do you enforce that restriction?
I'm not sure. So in the syntax, you can only write that with something with an uppercase here. So that's a very easy restriction to enforce. Okay. Even though X as a term has type lam, you can see from its I'm using the Ocampo convention that terms and term variables are lowercase, and something uppercase must be something weird and different, and you can tell it from the syntax. Another way to think of it is there is a distinct namespace of these kind of nominals, okay? And so when I apply something, I can check in the past. I mean, my program, I know whether this is a nominal or some arbitrary term, also of type lam.
So can I?
But you've got constructors beginning uppercase, but nominals are distinct from constructors.
So I put them in the same syntactic category. Yes, I would say they have distinct namespaces. Yes, it's a surface syntax question. I think if you had a constructor named X, then anyway, yes, let's say they have different syntactic categories. What would actually happen in practice is if you introduce a name, also X, it would shadow the constructor, and then you would be maybe in trouble if you want to use the constructor, so don't do that. But for the purpose of the talk, let's consider it's a different syntactic group. Maybe funny quote X instead of just X or anything you want.
Okay, so things of type lam that are not nominals begin with a small letter, and things that begin with a capital letter are nominals.
Yes.
Okay.
But and it's also a valid expression at type lambda, so it can be used.
So just to check I'm understanding.
Yes.
So each type can potentially be inhabited by a nominal
That's a good
if it's
question.
been introduced at the right place.
So there is actually a restriction here that I haven't shown. I'm assuming that A. No. The answer is no, but it's a part of the design that is not fully fixed. The idea is it wouldn't really make sense to have nominal at the type bool, for example. So I think you want to distinguish in the syntax and in the way you think about your types. So first, only data types can have nominals at their type. Okay, you think of it as an extension of ML data types, algebraic types. there is no nominal at of ML function type, for example. And I think it's still interesting to distinguish closed data types and open data types, and open data types being those that can contain the thick arrow and can be the domain of a thick arrow. So maybe I should change the syntax to be a kind of open type or bound type name to say, okay, here it's obvious because it contains a thick arrow, but to say you are allowed to abstract on this in a binder position. And in particular, the A here cannot itself be of the form A to B, for reasons that will make sense when I talk about the compilation. So A has to be, so yes, you give names to things that are ground in a certain sense, that are like data plus names.
Okay, and I have another question.
Yes.
Just to see I'm following. So the way I should think about it is that I have terms in context, but context has all the variable names, but that's implicit. But those big X's are some specific chosen subset of those that I can refer to.
That you know about statically at this point of the program.
Okay.
And nab is a way to capture things
Some of
coming
them,
from the outside and give them a name that you can use locally.
Thanks, sorry.
And then you can ask yourself, what if I want to represent this thing, okay? It's a lambda term that is built by the substitution of a free variable x. It's a closed lambda term, but still it's talking about this x. So you would write something, and what should I put in place of the question mark here? And the natural idea is to say, well, okay, let's make up a new construct to introduce fresh binders locally to bind names in expressions. Okay, and the suggestion is to use new name in an expression. So new x, and then I use x here.
I expected you to say now.
No, nab is a pattern matching construct. New is an expression construct. Nab is to say I'm matching on a name defined somewhere else that was sent to me. New is to say I'm creating a local name here. And this reduces to that, as you would expect. There is one thing that is unfortunate about it. So, okay, creates a scope in which nominal x is available. What's unfortunate is it's an effect, and as everyone knows, effects are kind of bad. Because you have to do escape checking. Okay, it would be terrible if x escaped from here, because then it would not be a name bound somewhere. It would just be a crazy free name, and you don't want to know that. In the logic programming community, they can talk about names and they check for escaping. So you have to do the same here. And so here you have to check that the expression here does not contain the name x. It's not escaping. But in some cases you use new, many cases you use new, and the result is at the type bool or int or something. And you know that these types are not inhabited by names, so you don't actually need to check. So that's also why I was pointing out the fact that it's useful to keep in mind that there is a difference between values that can be binders or contain binders and those that cannot. Even though, of course, if you have a list of something, you still need to traverse the list to check it. So trickiness coming here because of new. No question? No. Yes?
Well, what happens if you have a pattern? You said nabla xy in something, and the pattern doesn't, in some pattern, the pattern does not actually bind y, and then you return y on the right-hand side.
That's... so... That's a good question. I think currently so you could rule that out statically. I mean, it's obvious. But maybe there is a way to give this a meaning by saying this can capture anything. No, I would rule that out statically, but we might, we probably don't in the content notation. We'll be able to check in just a moment. And hopefully, yes. Okay, let's keep that question in mind for the end of the. So coming back to the substitution, people were saying, oh, but it's partial. That was Philip, because you have to assume that the second argument is a variable, and what is if something else? Indeed, it's not very nice. So let's get rid of that. And remark that if you have a scope system or type system for scoping, where you don't talk about the type scope, the types just about the variables, you can give this rule to the substitution principle that says, well, maybe x is free in T, but if it's not free in U, then the result does not contain x anymore. Let's use this idea to define subs with a different shape, saying, okay, T contains a binder, okay? Or rather, instead of T, I'm going to take a binder for an X and a T that contains X. Okay? So this now has type. It's not a lamb, it's a lamb, thick-arrow lamb. And U, of course, is not in the scope of this binder. That would not make any sense. So it's separate. And then I return a lambda term. Okay, so it's implementing this idea. So it's rather easy to do, but it's a bit, the typing is more interesting. So here, I'm pattern matching on things of this thick arrow type, and I can use in a pattern this introduction connectives, which is a way to remind you that these are not functions, okay? They are data. So if this is the variable, the nominal x under the binder x, return u. Okay?
If you say nav first?
No, because this occurrence of x is bound in this occurrence of x.
But it wouldn't be appropriate to write x on the right-hand side here, would it? It's only a
yes,
button.
x is not in the scope of the right-hand side.
So this is a difference between this and the nabla, right?
So it is a difference.
Yeah. I'm not saying that.
It's not the only difference. So yes. So here I'm saying I'm taking a value that is a binder, x dot, and then the body is x. So I'm only binding x locally, and I cannot talk about this x on the right-hand side because it would be extruding a name out of this binder. But you can mix your two favorite friends with this clause,
So,
which has a nab and an arrow.
So in nominal sets, that will be the square bracket, say, we don't know.
If you say so. So here I'm saying, okay, under the binder x, I get some y for a y that is coming from the context. Okay? So this is the case where the variable, so t, the term that is under the binder in t is a variable, but not this variable. So you just return it to judge. And here, y is bound in right hand side because I use nabla.
Thanks.
Yes, okay. In the add case, you do a recursive traversal. And notice that I'm using the application, the add construct. So if I had just had m here, this would be of type lam. And I have m at x, and then m has to be of type lam to lam. Okay, like thick arrow lam. And what this means, in a sense, is I have a term, I'm talking about x here, the rest is as if I had carved out the occurrences of x to be here, and it's a placeholder for where the x's are in the term plus the rest of the term in M. And so I can call my step recursively, and M has the desired type lam to lam.
Okay, but m at x has the type lam, right?
M at x has the type lam.
Okay.
And this x is this x that is bound. Okay? And are you sure there is no question?
And x doesn't actually have to appear in M, it's just that it might.
Yes.
Okay.
And then here's the last case. There are different ways. In a sense, I could do an eta contraction here. I have an x outside, inside I have an app, so there is another binder in the app, y, and then let's count all the occurrences of x and y out of R, so then I get something that has type lam to lam to lam. Okay, it's a lambda term under two binders, okay, and then I'm going to perform the substitution, going to map my substitution under my abstraction. So I abstract over another y, okay, different variable. And then in the body, I want to substitute r. So what I want to substitute is, so this is r at xy, or this y, under the name x, under a binder for x. Okay. And then this is. So here, I could actually write only r at x for this pattern, and write this here, and it would be the same.
And if both places say you wrote xy, you wrote yx, that would still do the same thing?
Yes, but if I write xy here and yx here, I'm implementing a different operation. Yeah, I should maybe have said this is the same as r at x at y. Syntactic sugar. Yes?
Could the x and y on the right-hand side have different names? For example, a and b.
Yeah.
On the right-hand side of the
arrow. Yeah.
Here?
yes.
Oh yeah, I could use a and b. Yes.
Yes.
Or yeah, z and z prime. Because y and b, a and b would be kind of weird. But yes. So yeah, a comment on. Yeah, no. Later. Okay. Yes.
It sort of feels like you are doing a substitution on a like eta expanded term.
Yes. Yes. Let's discuss that later. Yes.
Is there a variant language design where subst is just built in generically?
Yes. In particular, if you remove the restriction that you only in expressions. So in patterns, you will only ever be able to use nominals here. But if in expression I let you use any term, then that would be substitution.
Yeah.
But the point is that substitution, a name for another name, is doing nothing at all, essentially. Whereas substituting a term for a name is a runtime operation. So here, the operation that you see are cheap. And if you want to implement something, if you want to do something expensive, you have to implement it yourself. So the cost model is clear. If I use instead n at u, it would be doing something subtle, like traversing a lot of data. And maybe you wouldn't think about it. So we've been going back and forth on some of these design decisions because of this kind of having an effective cost model in mind problem.
I really like the idea of not needing to define subst.
Yes, you could also have, you know, these nice things called type classes, and then deriving, and it will be done for you.
But sometimes you might want to define
Yeah, that would be okay.
capturing substitution on some places, and you won't have that freedom.
Okay, let's give a last example. Now that I've defined this nice subs form, show an example where it comes up naturally in exactly this form, which is beta reduction. Okay, beta reduction, reduce t. Well, if it's just a name x for some x, reducing to x. Yes, if it's an abstraction, let's reduce under the abstraction. And here you see this kind of open the y, plug the y, dance that we've been doing several times already. So notice I used, at first, before I started working with product, they were using lowercase x's for these nominals, because in the product community you use lowercase stuff. And my opinion is that it's really like a new constructor, okay, of this data type that is added on the fly when you start talking about it. So I like the fact that it's uppercase. I think of it as an extra constructor that is only available in some scopes. And then in the application case, first you reduce both sides using shadowing, cool. And then you match on the left-hand side. If it's an abstraction, here is a nice part. You do a beta reduction again. Oh, this is deep, strong beta reduction on the result of substituting n in R. And R here is exactly what you want, lam to lam. You use this nice substitution. In the other case, you just build the neutral term that applies, and we are done. Yes, maybe a comment I forgot to make on the substitution is to use this substitution, you do not need to use new. Okay? And I pointed out before that new requires some escape checking, occurs check. So it's kind of a dangerous operation in the sense it introduces dynamic failure. So I'm not actually sure how much new do you need. So in particular, if you are willing to write even more boilerplate code than just subs, you can always define your own. You can define the function that for you takes a lambda term of type lam to lam, and checks that this binder is never used in the term, and it returns something of type lam. It's like this substitution, but instead of finding a U, it fails in this case. Okay? So then you can actually implement the new operation yourself with this kind of style. Is it something that you want to do? How much do you need new? Can you always use this kind of trick to not have to introduce free variables? I don't know. These are questions for you. Okay, let's go back to this question of eta that Philip had. Okay, so maybe we have a question on beta reduction. I think it's kind of cool to have 2 slides and correct capture avoiding substitution and beta reduction that looks nice. So, yes?
In many of these examples, if you just left out the line with nav, would it give you an error saying no, matching is incomplete?
So that is a question that Philip asked previously. Currently, we don't really know how to extend the exhaustiveness checks to support the fact that you can have new constructors that occur in the middle of stuff. So no, we don't know how to do that. And it's a very good question because exhaustiveness checking in algebra data types is super important. And the language that don't enable the warning by default are super misguided.
So your language is misguided, or?
This one, yes.
So by that definition,
It's experimental, it's don't count.
That's fine. Yeah, research platforms are important.
So pattern matching. Let's go back here. I made the point that the fig arrow is not a function arrow, that this is not a lambda abstraction, and that this is not application. But still, let's say if you thought of them this way for a minute, like a different arrow application and lambda abstraction than the one we usually use in ML, just for the binding function, you would notice that what pattern matching of these things is doing is a kind of higher order unification. Okay? So more precisely, it's unification modulo alpha, so renaming of binders, eta, as Philip pointed out, and beta 0, where beta 0 is a nice principled restriction of beta, we don't like beta reduction, where you are only allowed to substitute variables, not arbitrary terms, as I discussed, and furthermore you assume that the variables does not occur already in the term. So very, very strict fragment of beta.
This lambda is your slash.
Yeah.
Okay.
Yeah. This lambda is my slash, and the application is my at.
Okay.
And the lowercase x are actually
Bigger, yeah, okay.
But here I'm talking in terms of the lambda you know. So this idea of doing unification modulo with 3 things and nothing more implies 2 behaviors that are related. The first is that when I'm writing x at x1 at x2, you know that x1 and x2 must be distinct. It would be, you get a static error if you write at x, because x2, so this is the same as r at x1 at x2. So x2 by this rule has to be, to not occur in r at x1. In particular, it has to not be x1. Okay? And by r at x1, I don't mean the result of substituting, so it doesn't matter whether the binder actually is used in r or not. R at x1 is a term that contains x1. And then also, as I said, when you write r at x for the same reason, x cannot occur in r, and this is what we implicitly assume. This is required for the correctness of this line that we wrote, where we say, oh, app of m at x, let's just substitute m u. So if some of the occurrences of x were still left in m, pointing to this binder here, it wouldn't actually work or make sense. Okay, so here when I write m at x, I'm really separating on one side the x that I know, and on the other, a binder that is completely free from occurrences of x. It wouldn't even make sense to capture this m out of the pattern otherwise. Okay? So unification modulo this rule is called higher order pattern unification. Some people also call it Miller's pattern unification. And we have experts on this kind of higher order unification in my group. And it's decidable. It's even like with beta 0, it's easy to decide, and it has mostly the unified. I mean, which means that it's sensible to use it as a pattern matching mechanism. You are not adding arbitrary unification to the model.
Are those implied restrictions checked at compile time or at runtime?
So, there are some restrictions. So this does not imply restrictions that are checked at runtime. This implies restrictions that are checked as compile time, like the fact that these two binders are not the same. And I would say it's also, when you do unification modulo, a stricter set of rules that changes what can possibly match. So it's something that you rely on when you write programs. If tomorrow I change this and I use full beta here, some programs would maybe not behave anymore in the way you expect, and you would be surprised. So it's not only about forbidding things, it's about providing a mental model of what's going on to the program. So now I'm almost done. I'm going to say a bit about how the implementation works. So it's done by doing an interpreter in Lambda Prolog. So this slide is just about ML, not MLTS. So as you know, ML admits type erasure. You can forget about the type annotation and give a small step operational semantics to the untyped terms. Okay, small operational semantics, small step or big step or whatever, are one thing that are very easy to write in Prolog. So you can do just that. So this is a fragment of the way it's done in this implementation. So I've defined, so Lambda Prolog has this very annoying syntax. Kind TM means the kind of TM is type. So this is what we think of as a type declaration. So if the keyword is kind, it means type, and if the keyword is type, it means term. So the type TM has kind type, and then you have all these things which are term definitions. So actually these are constructors, okay? So I'm doing a deep embedding of ML into Lambda Prolog. So the add constructor takes two terms and returns a term. The lamp, so this is application in ML. This is fun in ML. So, and this takes a higher order, so term to term arrow in Lambda Prolog, which is a function, and returns a term. So this is, if you want higher order abstract syntax. The type of let is term, term to term, term, and then match takes a set of clauses, and I haven't here shown you what clauses are, but you get the idea. And then one easy way to make data types work is for any type declaration that you see, you declare a bunch of constructors in this type. So if I see a constructor K declared, I emit, so it's a compiler that generates, yes, let's think of it as a compiler from ML to Prolog that generates this kind of declarations on the fly, and then creates a deep embedding of the program and runs it. So if on the ML side you define the constructor K with so many parameters, I'm going to make this declaration of the type of K that has term, 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 to term. Okay? And then to define the actual semantics of this program, you define two functions. So copy is a way to define substitution that is nice and cool and I'm not going to talk about. And eval is a predicate that relates a term to the result of its big step evaluation. Okay? And I've shown you one case of eval here. So if you want to eval or let with a definition and a body, the value of let def body is VB, like body. If when you eval def, you get VD, and then when you eval the body in which you plug VD, you get VB. So the body here has type term to term. So body VD has type term. You reduce that and you get VB. So this is the big step reduction rule for let. Okay? And there is a one-to-one mapping. I have to stop. Okay. I have to stop now, or I have a minute?
Gently.
Gently, okay. So the way you extend it to MLTS is to add a bit more types. So something that is a binder in the MLTS world becomes a function in the Prolog world. So not everything is mapped to a term. Some things are functions. And then the mapping is mostly the identity, but be careful. This is the real lambda, and this is the real application on the Prolog side. Okay? And for example, new is like that, but I'm wrapping up. Okay, so there is an evaluation rule for. Oh yeah, let's do this before I conclude. The evaluation rule for new is using pi, which is deconstruct of lambda prolog that introduces a name. So introduce a name x, and then to evaluate something under a new t, introduce a name x, and then eval t of x, and you get a v. And there are two things to note. First, the v occurs here outside the scope of the x, which means that lambda prolog will check that x does not escape through v. Okay, there is this check occurring. And the other is that if you think of proof search as computation, the way to introduce a new name x is to do the proof search of the pi constructor, which is kind of super cool. Okay, so with this amusing remark, I'm going to skip the demo. I'm just going to show you how nice it looks. You see, this is all kind of code using LP, lambda prolog implementation, nice web stuff running in your browser, my browser. And it was implemented by this, and I'm done. And some of the future work is to find out how do you do pattern matching exhaustivity in this work. So sorry, Philip, no answer to this to your question, only questions. And then maybe, oh yes, so I've shown you an implementation translating all the functional stuff into Prolog, and then the naming stuff is just the magic of lambda Prolog. And what I would like to do is to take another implementation, translating all the functional stuff to functional programming language, and explaining away the magic of names. For example, by giving a standard small step operational semantics where you represent the names that you have generated so far in the environment and so on to for people like Ohad to be able to think about what's going on.
But it's there anyway.
And myself. Thank you. Sorry for the time. Do you have questions? Yes.
That's very nice.
Thank you.
It relates a lot to things like Pitts nominals.
Yes.
But is it exactly Pitts nominals but implemented, or is there a new theory here? Where is the theory written down?
So, no, I think it's not exactly Pitts nominals. That's, I mean, related to the question of Ohad or maybe well, one of these people here. I'm sure the meta theory is different. I'm not sure. So, could you justify the soundness of this language using Pitts nominals? Probably.
I think so.
Yes, that sounds something believable. Maybe you could also build the formalization of Pitts nominals in Abella, and then you would go the other way around. But I would say there are different meta theory. In terms of where is the theory of that defined, I have some big step rules here that sort of give semantics for the language, but they are not the meta theory of lambda prolog itself. But there is a point to a paper there.
So this is nice work. One thing I'd encourage you to do when you write it up is draw some of the lines between what you're doing and the existing theory.
Or just also draw syntax trees. Just draw it. It would help a lot.
Yeah, no, I agree.
I suggest we move the rest of the questions to the coffee break. Thanks, Gabriel, again.
Thank you.